So one thing I want to sort of touch on before we move into the rest of the course, because we're firstly going to touch on, we're going to go into sort of like writing C code. And C code, since it's a very like low level language in that you're dealing with memory, it's also sort of useful to understand how the code's compiled because of the file structure, and then how this file is then put onto into memory or loaded by your kernel on your laptop to be run, or how it's loaded into memory on an embedded system to get executed. Because we'll be looking at the boot up process of embedded systems and just running programs in general to sort of complete the picture, right? Because this is something that's usually not really touched on when it comes to learning about just writing programs. Like people, they just run a program, they don't actually really know what's happening. And so we're going to try and touch on this stuff lightly to give a bit of an understanding. Like we're not going into the ins and outs of compilers or anything. I also don't know this much about compilers like on that super low level. But we'll touch on quickly like the general process. So when I talk about like compiling code, just the title of this lecture, really it's a large and complex process. And so it sort of is like the entire building of a project, the compilation process, because the compiling or the compiler is only one small portion of the whole process. But we'll look this diagram sort of shows the entire sort of ecosystem, the files that are generated, and how the data is passed between various little components to actually come up with these executable files or libraries here, like the output, right? And so let's take a quick step sort of through it. And so what we'll see here is the input to the entire system, or really like you can see this box here. And so this is our building, sort of like the tooling and the temporary files that will get used to build our process, build our program. But what we're going to be looking at firstly here is this make file. And so like what is a make file? And you'll see them when you're building like the code that we'll be using in this course, or just in general when you're building C code. Because a make file is sort of, it's an old legacy build system. It's still used and you'll still see them, but it's essentially a make file is a script that enables GNU Make, which is a like a build system, to compile files and to link them and then to create programs. And so when you see a make file, and generally it will have like a list of source files and sort of the libraries it needs to link and all of these sort of complex command line terms, and essentially automates the building process. So it makes it a lot easier for you. So if I write 100,000 lines of code in 100 different files and you want to build it, you have no idea how to build my project, but I'll probably just send you a make file where you just run make on your command line and then boom, it's made. Now, so this is what makes it much simpler to build large and complex project with. But the thing is that it's quite old. Like, I mean, I don't know when it's actually from. I haven't Googled this. But I know that this sort of the generation of computer scientists before me, so they're the ones that used to write make files like pure. I mean, they still happen, and especially with like large legacy projects like the Linux kernel is still all in make files. But that's because this project is 30 years old. And so instead of scrapping the build system, they just update it, right? And so writing make files is still done, it's just not as common. The more common ways for doing especially simple, quick projects, like what we'll be really using in this course, we're not doing super large, complex projects. Using programs such as CMake can be used to generate the make files. And so you'll see in the code that we use, we have this CMake sort of essentially script, where we tell it in a sort of a more abstracted way what we want done and what files we have and what needs to get built, like which executables, and then it will generate a make file for us. And so this make file is generated by CMake, and so CMake's kind of taking care of the sort of the complexity of putting together all of the building bits, because make files are quite a bit more complex than CMake, and CMake is nice and easy to understand. So it's just a more modern version. But this is an argument that also computer scientists will get into about like what's the best, blah, blah, blah. I'm a big CMake fan. So this is what this make file is here. So essentially this make utility is what's getting leveraged to do all of these processes using, for instance, GCC, like which is the GNU compiler collection. And so in there is a linker and all of the things that you need, an assembler and a compiler and a preprocessor. But the make utility is being scripted by a make file to carry out these various steps. And so we can sort of look at these steps and we'll see that there are actually sort of like 4 main steps in the whole process of compiling like a binary, even though the compiler is actually only one sort of small step in the process. So the input really is, apart from the make file, which you don't actually need, like you can type onto the command line the actual compilation like instructions, and if you're doing like a single file program like Hello World, it's very easy to just compile it by typing in like GCC and then putting in the output file and the input file, and then boom, you've compiled your project. But when it gets to compiling large amounts of source files that all sit in different folders and you're using libraries and blah blah blah, then it becomes a lot easier to just do this via make files, because you don't want to be typing in the commands to compile 100 different files by hand. I mean, it just takes too long. But the input really to our project, apart from the make file, are these source files. And so you'll also, for instance, see assembly sources. I mean, in some projects, especially in embedded systems, you will see assembly files like this .s that are used for sort of hardware specific stuff or super optimized code. So on an embedded system, you'll usually see, which we'll get to when we talk about the embedded boot process, that there are usually a sort of like a reset code that is written in assembly that the embedded board runs it at startup. And so this is written in extremely low level, so directly in ASCII assembly, that it sort of instruments the board through its boot process. And so these files, you do see them in projects sometimes, and they also appear in other projects. They usually appear when you're dealing with sort of like hardware, or when you're dealing with something that needs to be super optimized, such as like really speed critical processing of things. People will write small chunks of code in assembly, like usually not very much, because assembly is extremely tedious to write, and also there aren't that many people, let's say like the average computer scientist or the person who works with C isn't really that well versed in assembly. Like myself, I can understand assembly to a certain degree. I mean, understand what's happening in it, but I've never really written portions of my programs in assembly. It's just not something I've ever required. But the most common one are obviously your C headers and source files, so your C files, your header files. If you're dealing with C++, you've got your CPP files. And then as well as like a linker command file, which is sort of really important, especially when we talk about this embedded boot process again, because the memory structure of your program is very important. And so you can sort of make sure that the memory structure of your binary that you generate fits with the memory structure required by your hardware architecture. But we might touch on that a little bit more when we talk about the boot process, more so than the actual the compilation process. So then we have these 4 steps. So we've got our input, and then we sort of, there's a bit hard to follow the flow, but if we ignore this archive utility, because it's sort of, I guess it sort of exists or it belongs to the linker in a way, that we have this preprocessor, the compiler, the assembler, and then this linker and locator. So I'll just call this linker and locator is really just called the linker, because it locates and links, like sort of library files, which you'd find from, for instance, the .as that you'll find, or the .libs that you'll find on your system. So if we'll just quickly jump into the first one, which is the preprocessor. And so as you can imagine, and from what the name sort of implies, it's something that happens at the very beginning. So it happens before the compilation. It pre-processes your ASCII source code files to make them ready for compilation. And so this sort of, if the pre-processing of like the C preprocessor actually does a number of different things. And so I will link somewhere in the course, or if you find me on GitHub, I have a Git tutorial repository where I really go a bit more into depth. I do a bit of a big write-up on all of these different steps. So I'll try, if you're more interested in that, then go and check that one out. But otherwise, just a quick overview of what the preprocessor and what the other steps do. That the preprocessor is sort of dealing with the code. If you think about a nice abstract way of thinking about it, it's dealing with really on like a text basis. So on like an ASCII source code level. It's not compiling machine code or assembly code. It's really just doing processing of your text files and handling these hash directives. And so these hash directives, what they can do is they can sort of give the preprocessor a heap of directives that carry out certain actions, namely the includes, which I'm hopefully, if any of you have written any C code before, you'll be familiar with, which is where you're sort of saying, hey, I want to use the functions in this library, and you include the header file, which tells you about the library, which we'll also get to more when we talk about the C language. But what it does, although it really just does a, where I've got it here, so one of the points here, this point here, The includes really do a copy and paste, if you will, of the specified file into the location where it is. And so this is generally used for including library functions, but it can also be used if you want to put like some large, let's say like a hex dump or some sort of random long char array that you have in a file. You can use the include directive to have that file's contents essentially pasted into wherever this include directive is written in your files. And so in that way you can think of it, it really is just like an ASCII copy paste. And so it sort of pre-processes your files and it generates these ASCII intermediate files. So if you can manually invoke the preprocessor and it will generate .i files, and if you look into them, they're very much still human readable. Your main.c might end up being tens of thousands of lines after it's copied all of the include files in, but it's still human readable C code. But before we get too far away from this little list here, then we have the hash define. And so these are things that we'll all touch on in the C lecture again, but a hash define is also another preprocessor directive where you can give some human readable token or identifier some value. So if you wanted to, for instance, you could say hash define pi, when you're dealing with the circumference or when you're just generally dealing with circles, you could do a hash define pi and then you put it as 3.14 whatever, and you can put as many digits as you want. And then every time you use pi in your source code, the preprocessor will then go and find this keyword pi and replace it with the value that you defined. And so it's sort of doing like a search and replace, if you will, on like an ASCII text. And so it'll replace, when you look at your .i file, everywhere that you had written pi, you'll see 3.14. And so this has benefits such as let's say you want to change the value of pi, all of a sudden you're like, no, pi is definitely not 3.14, it sounds more like 4 point something. Then you can go and you can change this define value and then recompile your code, and this value will change everywhere. And so it really makes it easy to change one value all throughout your source code without having to go and change each one manually. So that's a very much a very nice thing for maintainable code, but it also means it's more human readable because you're having ASCII keyword sort of tokens instead of random numbers. Similarly, the ifdef is a preprocessor directive used for doing conditional statements within your preprocessor. And so you'll commonly see this used in large libraries or sort of configurable things, as for instance, we'll be using later in semester free RTES, which is a real-time operating system. And it has lots of different features and functionalities, but you might not want them if you're not using them, then you don't really want to include them in your program because you've just got this extra code that's taking up space, making your program slower and not doing anything. And so a really common way that ifdefs are used in C programs is that you'll have sort of if you've defined use semaphores or use amazing feature, then the code within the conditional will be compiled and included. So essentially the preprocessor will go through and evaluate these conditional statements, and if they evaluate true, then the source code is left there. If they don't, then it sort of ignores it and it gets rid of it so it is not compiled. And so you can sort of use this to handle the actual exclusion of code from your final C codes, these .i files that are then compiled, right? On top of that, with the defines, you sort of have macros, which are sort of another, not so much a search and replace as such, but they're more of like a search and replace, but it's like a function in that you can pass it in a variable. So you could use it for really easy initialization of enum arrays and stuff. And it's got a lot of complex uses, but I think it's something that I don't really want to touch on here, but there are sort of other preprocessor directives. But the most common ones and the easiest ones to understand definitely include just the standard copy and paste define and the ifdefs, which will also come across quite a lot. So that's the first step of the process, is that you get your C files, your C++ files, and then your header files, and you sort of do this copy and paste and get rid of stuff and whatever, and then you create these final .i files, which you never really see. You can go into them if you want and sort of check them out, but this stuff all happens under the hood. And then these files are the ones that are then ready still in ASCII C file format, and these are the ones that are then passed on to the next step of the process, which is the compiler, right? And so this is where you can see it here. Some C files won't need pre-processing, and they just go straight into the compiler, but generally, I mean, you'll pre-process them and then pump them into the compiler. And so the compiler is the next step, and it really does, I mean, what it says. And when people say, oh, I'm going to compile my program, like, compiling is the small portion that is done by the compiler, and this is where we generate object files. Or essentially, the compiler doesn't even generate object files, it compiles .s files. And so these files are an intermediate between the ASCII C code and machine code assembly, which we get out of the assembler. And so what it does is it takes our ASCII C code, which is just normal, what we write pretty much, or what comes out of the preprocessor, and it turns this into what is known as ASCII assembly. And so this is, I think I'll have like an example maybe somewhere, no. So like if we've all seen assembly code, like with these like LD and MOV and all of the different assembly instructions, it turns your code into a file like this. So it's still in a way human readable. Someone that's got a good knowledge of assembly can look at this file and understand what the program's still doing. But it's sort of just an intermediate step between going from ASCII sort of human readable like semantics and machine code binary, right? And so this is sort of one step in the process. And so what the compiler actually does is it does a number of different steps, and it sort of parses the code and slowly breaks it down and optimizes it. And so the first thing it does really, and this is something we'll definitely touch on in the C programming lecture, is there's a lexical analysis of it. And so this means that it finds tokens within the code because of how compilers work, and they have essentially a grammar language where they have a bunch of sort of grammar rules that they have to that they enforce, but they're not so much caring about what the variable is actually called. They just want to know where it is and what sort of operators are being applied to it. And so this lexical analysis essentially takes apart your code and finds all of these different tokens and says how, yep, here and here are the same token used in here and here, and then it comes up with this sort of grammar or this language representation, like a lexical representation really, of your code. And so once it has this lexical representation of it, it's very easy for these sort of language grammar rules to be enforced for semantic analysis, meaning that it checks that the semantics in your code are correct. So for instance, if you had a typo and you have then accidentally created, like put the wrong token ends up somewhere because your variable's named something wrong, different, the semantic analysis might find that, hey, you've written here by accident invalid code, and it'll throw an error sort of thing. So the semantic analysis checks for the correctness of the code once it's broken down into tokens, right? And so what then happens is that the code is sort of turned into a bunch of little steps, if you will, in that the instructions or the human, like we can write really complex single line code statements. Like if you just think about maths, I can do A plus B times C minus 3, blah, 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 and we have this super long math, but even if we as humans want to work this out, we still do it in steps. Like, you know, like in school, you do inside the brackets, and then you do multiplication, and then you do subtraction, and there's like a step to it. And so this intermediate code generation does exactly that. It sort of takes these complex single liners, all these complex operations, and breaks them down into steps. Because as you can imagine, when we're dealing with machine code assembly, all of these like additions, these multiplications, these come down to essentially the addition of two numbers or the multiplication of two numbers. And so we can't have these super complex long operations, and we need to break it down into the individual steps. And so that is what this intermediate code generation does. It simplifies the code in a way and makes it in and puts it into a representation that the compile, the assembler, can then more easily turn into assembly machine code, right? And so once we get to this point, we're at a point where we've already simplified our program in a lot of ways, in that each individual step of the program is much simpler. And so therefore, if we, by this simple sort of representation, it leads to be more easily optimized. And so this is where we can sort of bring in the first step of the optimization solving, because the compiler, and one thing that you'll really get presented with a lot in the world of like C development, is like compiler optimizations. People always say, oh, when you're using compiler optimizations, this might happen or this might happen. And so you can tell your compiler to optimize or to not optimize your code, and sort of different compilers do different sort of optimizations and whatnot. But the compiler, or compilers over the last 50 years or whatever, have gotten really good at making much more efficient and quicker code, because there's lots of small, low-level optimizations that can be carried out. And the first set of these optimizations happens at this point. Like once we've got this intermediate sort of simplified code, it can then go and say, hey, if we're using some variable that's getting set but never read, then a common optimization, which you'll see, and when people have problems debugging, like, hey, my variable isn't set, it's said optimized out. Because if a variable is set but never read, then the compiler thinks to itself, why do I bother storing this if no one's ever going to read it? And then it will just get rid of it. And so this is a basic, a very simple example of a compiler optimization. But then we get down to the first time we're going to talk about object code. And so objects are these .o files, and they become very important in the next step. But an object code is really creating exactly what the name sort of says. It's creating some sort of a code object. And so in this case, it comes from a source file, generally just one .c file, generates an object file, which is a .o file, and it exposes the functionality that was defined within the C file. So we'll say, yep, these variables are stored in here, these functions are in here, blah, blah, blah. And so we need to get to the point where we're actually saying, okay, we have these variables and we have these functions and these operations are being used and blah, 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 and we need these dependencies and I call these functions. And so all of this, this sort of what's the word for it? Creating this inventory of what's happening. This is this object code generation, and in here you'll actually give it within local to the file sort of memory location. So it'll go through and say, yep, I have these variables and we're going to put them in memory here, here, and here, and these ones are my uninitialized variables, and they'll go here, 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 and then these are my functions, and we'll put them in memory this one and this one and this one. And so it does this structuring of what the file contains in memory, sort of giving it offsets. And then, of course, we can then, once we have at this point, we can then go ahead and do more optimizations. So don't ask me what exactly optimizations are done in each sort of step, but you can optimize more, right? And so the thing that you'll see commonly referenced when we're talking about object files is a symbol table. And so when you're linking, especially, which we'll get to in the next step, when you're sort of compiling a program, you have all of these object files, they expose the things, the objects in them, not the objects, but they expose the variables and the functions. And these are referenced as symbols. And so a symbol could be, yes, this variable lives here, or this function call is here. And each object file has what's called a symbol table, which is essentially just an inventory or an index of the functions and variables and all of the things that live inside of that object file. And so we'll see in the next step with the linking, you can imagine if you had a program made up of two files and they had functions in them and they'd called each other, you would need a way for each of these files to know that, hey, my function exists in this other object file. And so this is where the symbol table comes into it, because the linker, which we'll see in a second, can then look at each object file and say, okay, hey, I need printf, and they'll say, oh, hey, in the printf C file, which is now being sort of compiled to an object file, printf exists there. Cool, that symbol's there, and we can sort of connect them or link them, right? And so this is a symbol table. It sort of tells us what is inside the object file, right? But before we get to linking, there's the next intermediate step. So here at the output of compiler, we have our .s files, right? So this is ASCII assembly. It's still in a way human readable. But now we're going to take it to the next step and sort of turn it into machine code, right? And so this is where we take the assembler, and then the name, as it aptly sort of represents, it takes assembly and it creates the output of what you'd expect from assembly, which is machine code, right? So it generates these machine code object files, which are the .o files, right? It does a few things, such as giving memory offsets to the memory location, sort of like you were saying in our ASCII, an ASCII assembly file. We'd have our labels that would say, yep, these are the variables, blah, 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 but then it turns these into actual memory offsets and whatnot. It also then tracks, for instance, these unresolved references, and I was saying we have a symbol table and that we expose symbols. If a symbol or if a function call that's in another object file is used, this is what will be called an unresolved reference. The file needs to be made aware that the function exists, but it doesn't need to know exactly at compile time where it is. the linker, which is the next step, takes care of connecting these two. But the object file needs to say, hey, I have this, I need to call this symbol, I don't know where it is, and then it puts it in these, essentially an unresolved reference, and the linker has to go and solve all of these unresolved references, and if it can't solve them, then you'll get a build error. And this is very common, like it'll say, unresolved reference to blah blah blah, did you forget to include this header file? And then this is because you forgot to include essentially the reference, or to do the preprocessor directive to include the appropriate library files, right? And it can also do things, for instance, as debugging or compiling in debugging information. So there's usually, you can either build release or a debug, and so a debug has a lot of extra information in the object files where, for instance, these memory locations, because at this point in our compilation process, everything's starting to just become numbers and memory offsets and stuff. There's not really any ASCII human readable stuff, but debugging information allows or puts in enough human readable information such that when we can go and debug our program, we know that it's a variable called this, or it's not just, and it's just not some random memory address, and we have no idea what's going on, right? So this is the assembler. It just essentially creates human readable. It's from human readable ASCII. It creates machine code ASCII, right? And then we get to sort of this step that's very important in the process, and it's also one of the ones that sort of trips people up generally when it comes to building big files or big projects. It's definitely something that I struggled with when I was learning how to put together really large or to take other people's project and to build it on my system, because compiling is usually pretty easy. There's like either some sort of some error in your code, or you've just typoed something, forgotten a semicolon. But the linking errors are really large, can be large and complex, meaning trying to get the right libraries and making sure that the right environment variables are defined in your path, and it can be really tricky, right? But the linker has the job of essentially taking all, we'll just move to the next slide, of taking all of these object files, these machine code assembly files, the .os, and creating an executable binary, right? So we have like some program written in 100 source files, so we have 100 .c files, means that we generate 100 .i files, which generates 100 .s files, and we get 100 .o files, right? So we get 100 object files that have the machine code of the source code, as well as the symbol table, saying, hey, I have this function and this variable here in my object. And what the linker does is then it takes all of those objects and these unresolved references, and it links them all up. And it says, okay, cool, this object file needed to use printf, which is in this source file. Cool, it exists, and we'll combine the printf code into our executable binary. And so these are commonly, could be a .l file, which we'll talk about in the next lecture when we're talking about sort of loading and running programs. But what happens is when we come out of it, we come with a fully linked executable object file. Now, there are different variants of this when we're talking about sort of shared libraries and dynamic libraries and whatnot. But just to keep it simple, when we're talking about sort of the code that we'll be using in this semester, we're just really looking at compiling just an executable object from the files that we have in our local directory, for instance, right? So it does exactly as I was mentioning before. It sort of connects these missing links, and a common error that you'll see, for instance, is if you accidentally wrote the same function twice. Like this, you name two functions the same thing. Your linker will complain, hey, I needed to resolve this link, but then I found that there were two definitions of it, and I don't know which one to use. Hey, you need to go and fix this up. So this is one possible sort of problem. And as you can imagine, it has all of these different object files, which have all of these different memory locations that have been allocated for all the different variables and functions. It needs to combine this all into one, right? And so this is a sort of a good little figure I found online. And you can imagine you have like your two C files here, which creates your two object files here. So they have like their code and their data, which means they're sort of like the code itself and then the variables. And so each one of these object files has its memory offsets within its file, but then we want to combine these essentially. And so what happens, we need to do sort of like two things. in that we can combine the sections, like we combine all the code together, and then we can combine all the data together. And so we'll see this a bit more in the sort of the program execution. I'll talk a bit more about what like the .text section is and the .data section is. But essentially you need to take all of your object files and take all the things that are similar, like, you know, take the code and the data, and you split them apart and you put them with the other counterparts and the other object files, and then you put this all back together into your executable object file, such that it's all structured in a nice way that you have your code here and you have your variables here separate, right? And so this is the general, what a linker does, is it takes these object files and it combines them into your executable object file, right? And so this is one thing that we'll touch on in the next lecture, which is the structure of an ELF file. And it's got all these different segments and whatnot, but we won't get into that yet because I'm going to do a lecture on that right now. So I hope this really helps. Just in general, the compilation process, or the linking process especially, is the thing that scares people the most about getting started with C. Because unlike Python, you just write your code and you hit run and your system has all the modules and it doesn't need to compile and it just runs. It's really easy. The C compilation process is something that I find really intimidates people. And I wish that when I was learning all of this back in my undergrad years, that someone had really gone through and told me how compiling works. Because there's really a lot of simple steps. There's a lot going on under the hood when we talk about compiling, optimizations, and all these sorts of things. But the process of linking and compiling is quite simple. And as soon as you understand what a linker, for instance, especially a linker, is doing, understanding your compile, your errors that you're getting when you're trying to build some code becomes a lot simpler. I used to look at errors of linking and be like, hey, this is not found, blah, 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 and I'd be like, what's going on? Like, my system sucks, everything doesn't work. But then it's really just just me missing some, hey, my code, like, you just need to point your system and say, hey, the code exists here, link against it, like link this code in, right? If you're having some library. Okay, so thanks for watching.